Welcome. My name is Scott, and I'm going to be talking about this propeller-powered IN-12 Nixie tube clock that I designed and built. So we have a couple versions of it. Here we have my original prototype and my completed revision 2. So Nixie tube clock is a clock that uses these sort of old school glass vacuum tube Nixie tube displays to display the time. There's lots of different Nixie tube clocks you can find on eBay. I decided to build my own after I built numerous ones from other suppliers. I incorporated a lot of the ideas I've seen from some of the other clocks into mine, but actually did do most of the design work myself. The sole exception is the design of the high voltage power supply, which did come from the Tube Hobby clock. This is a GPS synchronized clock, so it is always correct, always has the right time. It's in an acrylic case that I designed using Pinocchio to manufacture. Pinocchio is a company that cuts out your, well, Pinocchio is a company where you design things using a vector drawing program such as Inkscape, send it to them, they cut it out with a laser. Comes in a big sheet like this, and then your various pieces are all cut out of that. You take a piece out and assemble them and make your case. I'll actually show myself building this clock and assembling the case, soldering the components, mounting the tubes, all that throughout this video. Let's talk about a few things that make this clock unique. So this is the only one I'm aware of that uses a Parallax Propeller microcontroller. The Propeller is an 8-core microcontroller. It's programmed with a unique language called Spin. Really like using the Propeller. It's somewhat overkill for this project, as I think I only used like 3 of the cores on the chip to actually implement the clock. But it's a unique chip, and I like to use it. The power supply uses a TL494 switch-in mode power supply with an inductor, IRF840 MOSFET, big capacitor to hold the charge. Generates about 170 volts to power these tubes. The GPS is a UP501 module, got that from SparkFun. Always make sure that the clock is properly synchronized at the right time. So this was my original prototype, and doing the original prototype I learned a lot of things. One of them was I didn't put the right size hole in the PC board for these pins to fit the IN-12 tubes, so put a bigger hole in. Nice thing about the IN-12 is it does use a pin socket, so you can unplug it, replace the tube if tube goes bad. A lot of the other ones, like the IN-14 vertical tube, you have to solder in directly, be a bear to replace. There's also a horizontal mount tube. Other tubes are vertical mount. This one's horizontal mount, so the clock's going to have to sit up on its end. My original board, I used a DS1302 Dallas Semiconductor real-time clock. And, that worked fine, but it wasn't GPS synchronized. I wanted GPS synchronized, so I experimented with the UP501, wiring into an expansion header. All this wiring wasn't too convenient, so next revision I added a footprint right there on the board for the clock. A footprint right there for the GPS module. Underneath that footprint, there's actually room for the DS1302, so a person could build a non-GPS version of it. A UP501 is about 50 bucks, so it pretty much doubles the cost of the clock to have that GPS module. This one I put the power jack coming in the bottom. That wasn't smart because if you want to set your clock flat on a desk, power jack, wrong spot. What else did I change on this? I think that's most of the important bits. I did add I added another option for a header to get power into it in case you didn't want to use a jack. Maybe design one with a different kind of case, put jack out the back or something. That's about it. That is a IN-12 Nixie tube propeller powered clock that I designed and built myself. Let me show it off here in various lighting conditions. This is actually all of the lighting in the workshop at the moment. I can turn off these LED lights. I can turn off the desk lamp. Turn off the camera light. And turn off the room lighting. Now you're seeing it in the dark. Displaying time. All things considered, it worked out pretty good. Now let's discuss actually building the thing. Okay, so here I am in progress assembling the Revision 2 Nixie tube clock, propeller powered IN-12 Nixie clock board. So I always start by doing the low profile components first, so primarily that's the IC sockets. The nice thing about doing the IC sockets first is you put them in, you can simply let gravity hold them in place while you solder them. If you have a bunch of things sticking out, then the IC sockets will get crooked, fall out, etc. So I usually start with those first. The exception on this board is that I did place a few components hidden under this large 40-pin socket. That includes a crystal, a few resistors, and a bypass capacitor. So do those little things in there first, then hit the 3 IC sockets. These 2K155 drivers up here, those don't have sockets because I've placed them slightly underneath the IN-12 tubes. After doing the IC sockets, I usually proceed with resistors, so I have all of the resistors on the board, including this potentiometer. I have the diodes. This is our input diode, our ultra-fast switching diode, just a little switcher there. And the bypass capacitor, so there's a couple of those scattered around the board. So that is the board at this phase. Next I'm going to put in the transistors, the choke, and the TO220 voltage regulator and MOSFET components. Okay, so here we can notice I have soldered in the TO220 components. So we have a 5-volt regulator, 3.3 volt regulator, and a IRF 840 MOSFET. I usually don't bother with the screw holes on the top, lining those up, because I don't heat sink them or put the screws in, because we're not generating that much heat with the components in this this clock. Now, one thing I forgot to mention before is I have purposely left this area here unpopulated in this one that I'm building. The reason is that this can house either a DS1302 real-time clock and its associated crystal, it can house a temperature sensor, or it can house a GPS module. And in this case, I am planning on putting the GPS module on this board, so I am saving that for last. I will do that since it's rather expensive, after I've already tested the board and made sure that there's no problems with it. Okay, now I have installed the choke and the electrolytic capacitor. So this is the choke. It's a 270 microhenry choke. And we have a couple of small electrolytics, 10 microfarad, 16 volt will do on those. This one here, the size can vary depending on what your intent is. If you want to power it by an AC supply, you probably need a pretty big, like a 1000 microfarad or so. DC supply, something smaller, like 220 microfarads, what I have, might even be able to eliminate it altogether. And this one here is the high voltage capacitor. Now I tend to use 450 volt capacitors, even though the supply is only going to be designed to run about 170 volts, just to have lots of additional room on that voltage rating, because I did have a supply once with a either 200 or 250 volt capacitor, somewhere in that range, and I actually blew out the capacitor. So way overrated putting a 450 in there, but it seems a bit safer. So next, to finish this up, I'm going to do a couple little capacitors here for the high voltage supply, and then I have all of these transistors to put in. Okay, so now we have all of the components soldered except the Nixie tubes. So A few things I soldered since the last step include the programming header. It's up to you whether you want to put a right angle one in or a straight one. When I'm putting it in a case, I like to put a straight one in because I don't have to have a cutout in the bottom of the case for the angle one. I also put in the power jack. That came from Spark Fun, and it's nice that they have power jacks that have nice little pin size mounting pins rather than some of the ones that have tab size ones that don't really fit the hole in the PC board. So some of the PCB mount ones from Spark Fun are good. The other option is there is a pin header, unpopulated in this one I built, but there's a pin header right there that you could run power to. I also put in all of the transistors. There are some MPS A42s and 92s up here. It's important to put the right transistor in the right spot. It's also very important to face them the right direction, right polarity on transistors. Even though I know that very well, invariably when I'm building something, half the time I will solder one in backwards because I got in a hurry, and then all of your time is wasted desoldering that thing. The hurry wasn't worth it. It's also a 2N3906 over here as part of the power supply, high voltage supply. And down here is an unpopulated expansion header. We don't even need that. Also an unpopulated 5-volt output header. We don't need that. So next up is going to be doing these Nixie tubes. Okay, so my usual technique on soldering these tubes is to put the tubes on the, or to put the pins on the tube and then plug the tube with pins into the board. I've got the clearances a little bit tight on these pins, so that's not really working out for me this time. So what I've done this time is put the pins in first. They're all very loose in there, so if I flipped it over they would all fall out. Now I'm going to take the tube and carefully push the tube in. That makes sure all of our pins are straight. Now I'm going to flip him over very carefully. Then I'm going to solder, I think, just 1 or 2 pins per each one. That'll allow me to have some flex back and forth to fit them to the case. And that'll hold everything in so it don't fall out. So let me pause this while I take and do some soldering. Okay, so I have mounted all 4 tubes. I've soldered 2 pins on each tube. That is the top pin and the bottom pin. So that'll give me some flex before I solder the rest of them. I actually have 1 tube in upside down. Oops. But that shouldn't matter because we will be able to just unplug him, flip him over and plug him back in once we have the pins soldered. So this is part of the case that I designed at Pinocchio. So I'm going to take, it's a nice acrylic case, it still has the paper attached to each side while we work with it. So I'm going to fit it on there. That is going to hold all of our tubes straight. Then we're going to flip them over. Use a couple of these other chunks of Pinocchio case as spacers. One more. And now that we have all of the tubes properly spaced and straight, go ahead and do the soldering. Before plugging in the microcontroller or any of the other ICs that are socketed, we want to check some voltages to make sure they're right. So I have the multimeter hooked up to a ground, and I'm going to check up here for 5 volts. Got it. Over here, 5 volts. Over here we should have 3.3. Ground, 3.3. Ground. Here we should have the 3.3. Ground. Looks good. Okay, now it's time to test out our high voltage power supply. So I have plugged in the TL494, that's that big chip there. When you do plug that one in, make sure you do not have your board powered up. because this will enable the high voltage supply. You can get a nasty shock. So we'll plug in our transformer. I also have the multimeter hooked up to the output side of the ultra-fast switching diode right here, directly up from the MOSFET. So we'll plug in, and there we got 228 volts. We want to get it down to about 170, so we will adjust this pot. That's going up. This is going down, down, down. Doesn't have to be exact, but let's try to get close. Oh, come on. Uh, 170.5 volts I think is darn close enough. So we have our high voltage supply tested. We've tested the voltages to all of our chips. If we really wanted to be safe, we'd go back and double check and make sure our 3.3 volt supply is still doing what it should. Now we're ready to install our microcontroller and our other chips and program. Okay, so now we're ready to program. I've got the prop plug hooked up to the USB cable, hooked up to the computer. I've got the clock plugged in, so everything here is live and charged up. There's no output because we haven't programmed the chip yet. So I have opened up the source file. I've commented out the GPS clock portion of it and commented in a fixed test case, which should display 1245. So let me control F11 to burn it to the EEPROM. Verifying EEPROM. There we go, 1245. So it has lit up the test pattern. So I will comment out the test code, comment back in the GPS code, control F11, and now it displays 8. And the reason it displays 8 is because that is whatever random value is sitting in memory in the GPS code for when we're not actually talking to a GPS because we haven't soldered it on. So our board is all ready to go for the GPS to be plugged in. Take it to the other room, solder that GPS in, and see what happens. Here is our UP501 module. I have pre-soldered a standard header onto it because it's going to be much easier to solder this header on out of the printed circuit board than when we put it on and it's squeezed in next to that chip. So it is ready to go. Put it in, then we'll flip it over and solder. Let's see what happens. Okay, now it's time to actually do our final test on the clock. The UP501 module is soldered in place. So when I turn this on, it's either going to display a time on the display or turn a UP501 GPS module that costs 50 bucks into a smoldering pile of rubble. Let's find out. Plugging in now. 4:59. Let's turn off some light. That is not the correct time, but it is a time, and that's important because it's getting that time off the GPS. So what we need to do now is wait a while for the GPS to get sync with its satellites and download the current time. And I will come back in a moment or two once that is done. Looks like that only took me about 30 seconds worth of walking away, and when I walk back it is now displaying the correct time, 7:14 p.m. So it took that long for the GPS to get its lock on the satellite. We now have a GPS synchronized Nixie tube clock. The next task is to assemble the case for the clock. These pieces came off of a website called Pinocchio, which lets you design your own designs. Then you can send the files to them and they will laser cut it out of acrylic for you. So I designed all of these pieces in Inkscape. Each piece is a different piece of the case. Bottom, top, and then 3 that get sandwiched together to make up the sides. So I did do a little bit of Dremel trimming there to trim a slot for the power jack. If I would have been a little bit wiser, I would have probably had that in there in the actual design file. But a little bit of hand trimming didn't hurt. So let me put the case together and see what it looks like. Okay, so let's assemble the case. We've got the bottom, top, and the sides. The sides, I've already installed a hex standoff in each corner that holds the 3 sandwiches of side together. I also took the Dremel and did a little bit of trimming around where the power jack will go, so that our power will, come on, cooperate, so that our power will plug in as it should. Looks like it'll work. Next revision of the board, next revision of the case, I'll probably just have that in the design template, so it's automatically in there. And then I've just got a bunch of screws. So it's just a matter of screwing in these hex studs. Don't want to over tighten them. I'm putting these ones in very loose, because if we over tighten something, we could crack our acrylic. Probably should already put that clock in there, because sometimes it likes to fight a little bit. Oh! There we go. Clock installed. Top piece. That's going to work. Actually has a little chunk of acrylic still in it. Come on. That's what happens when you try to do a live demo of something. There we go. Clear of little chunks of acrylic. Now we can put the screws in. Take and snug them up from the back. Could get little rubber feet that were screw mounted and put them in and give it kind of a finished appearance. So I did design it so you could screw the circuit board itself down, but I don't think that's necessary because it's held in there snug already. So that's our finished clock in case. Plug him in. There we go. There's the unsynchronized time again. Turn off some lights. Let's let him actually sit here and watch the actual moment of GPS synchronization. That wasn't it. That was just a clock rolling over. Any day now. What do they say? A watch pot never boils. There we go. So it is currently 7:30. That is the time that I finished putting the GPS module together. You can see the GPS module managed to lock on, even though it's inside of a thick acrylic case with a high voltage switching supply right next to it and tubes and stuff, and inside my machine room with computers and walls around it. So I'm pretty pleased on that. Looks like it's going to keep excellent GPS time. That is the IN-12 GPS Nixie tube clock, propeller powered, that I designed. Let me shut off all of the lights for maximum effect. And I can give it a little bit of a slant, so the camera is looking at it. There we go. Another minute has gone by. Alright, that's it.